Lecture 1. In nanotechnology, when objects get smaller, their surface area gets larger compared to their volume. A clear difference in surface area between bulk and nano-level materials can be illustrated by the following picture. When a large sphere is split into smaller spheres, the surface area increases dramatically. Dimensional reduction will become massive when we get down to nanometer range. Just by going down from a sphere which has a diameter of 1 centimeter to a sphere with a diameter of 1 nanometer, going to lead to an increase in the surface area by more than 10 million times. It is evident that reducing particle sizes can have a significant impact on surface chemistry, but in this lecture, we are interested in what impact the particle size may have on space between the particles and how we can measure it. Assembling or consolidating nanoparticles in tighter agglomerates will produce a range of voids and shapes between the nanoparticles. We will generally call them pores. And as it is nanomaterials course, we will be talking mostly about nanopores. Sometimes it is very difficult to control the size and shape of nanopores created by using nanoparticles agglomerates, especially when it comes to nanopores of just 1 nanometer. Luckily, nanoparticles assembly is not the only way for creating nanopores. Let's have a look at other ways of making nanoporous materials. There are 3 common ways of creating nanoporous materials. First, there's a natural phenomenon for some materials to have pores of molecular dimensions. We say that the pores have molecular dimensions if they are close to the size of common molecules. Zeolites or metal-organic frameworks are 2 examples of these highly crystalline and organized porous materials. They have pores as part of their crystal structure, and these pores can be extremely small. For example, zeolite materials often have pore sizes below 1 nanometer. The material shown on the slide is called ZIF7, and it has regular pores of just 0.7 nanometer throughout the structure. Zeolites and MOFs are crystalline and organized in regular structures, with pores being in a perfect order throughout the entire structure. Although there are some ways to govern the properties and pore sizes in molecular materials, sometimes it is more practical to have larger size of pores and to have the pores in unusual shapes and forms. You can make pores of specific shapes and sizes by growing your material around a template. Some soft nanoparticles and micelles can be used to produce a highly organized network. If we can grow a solid material around it and then remove the template, we may end up with highly regular pores of shapes and sizes pre-designed by the template. The variety of options here can be quite significant. For example, here you can see the transmission electron microscopy image of a silica material. It has highly regular hexagonally shaped pores with dimensions of about 5 nanometers. This material is made by assembling silica around a template and then removing the template. We still shouldn't discard the simple assemblage of powders as a way for creating nanoporous materials. And this is our third method. In this case, the pores are just voids between the particles, and although sometimes they can be quite random, like for the material shown in the picture, the particle assemblies have their application in chemistry, especially in heterogeneous catalysis. With so many options around porous materials, it's time to classify them based on their pore sizes. According to IUPAC, which stands for International Union of Pure and Applied Chemistry, the first class of materials is microporous materials. These include all porous materials with pore sizes below 2 nanometers. Coincidentally, zeolites and MOFs are microporous. Here's, for example, a picture of a crystal structure of a metal organic framework. This one is known as MOF5. MOF5 has the largest pores among MOF materials. However, although considered massive for molecular materials, these pores are still under 2 nanometer, making MOF5 microporous. Unusually large pore size for a molecular material make it possible to see the pores with a good transmission electron microscope, as you can see on the left. The next class of nanoporous materials are so-called mesoporous. Coincidentally, these are often made by template removal techniques. They have pore sizes between 2 and 50 nanometers. It is often quite easy to detect the pore sizes of mesoporous materials using transmission electron microscopy. The example shown here is for so-called mesoporous silica, in this case, SBA15, which can be prepared as highly ordered structures with the help of a template. What we've got here is elongated porous tubes with hexagonal openings of just over 5 nanometers. Silicas, which have silicon oxide as the main element of their structure, can withstand high temperatures. Also, they are chemically resistant, which makes them a very popular choice in catalytic reactions. The final type of nanoporous materials, according to IUPAC classification, are macroporous materials. They have their pore sizes larger than 50 nanometers. It is common for macroporous materials to consist of particle agglomerates. However, the macroporous materials can be made artificially using top-down approach. For example, here's a scanning electron microscopy image of silicon etched with a laser beam lithography to give a highly regular macroporous structure. Finally, if you look across scientific literature, you'd have noticed what the pore dimensions will come in different shape and sizes in terms of units used. For example, molecular chemists who work with MOFs tend to quote the pore sizes in angstrom or picometers. In 1 nanometer, there's 10 angstrom and 1000 picometers. We've seen from IUPAC classification that macroporous materials could encompass a very broad range of materials as their pore sizes are above 50 nanometers. That means any material in principle can be considered macroporous. However, we will set the limit to this definition by aiming to keep our pores below 100 nanometer, or in other words, as close to definition of nanomaterials as possible. Fine powders with particle sizes below 100 nanometer will eventually form pores below 100 nanometers. For example, the electron microscopy image of silicon nanoparticles shown here is an excellent representation of a macroporous material formed by nanoparticles. The pores are just voids between the particles. Unless you have a very well-organized nanoparticles like silicon nanoparticles displayed in the image, the pore sizes may have huge distribution of sizes and pore shapes can be widely different. For example, needle-shaped or cylindrical pores are possible when fine powders are made of platelets. How do we even know what material is macroporous? Sometimes it's possible to measure transmission electron microscopy to determine pore sizes, but often it's not the case. Furthermore, chemists often would like to know some practical information about macroporous materials. For example, if you work in heterogeneous catalysis, you would like to know the specific surface area of your material, as most of the catalytic processes are happening on surfaces. Is there a reliable way that can help us to define the particle sizes as well as give us as much information as possible about the surface area at the same time. The common phenomenon of absorption occurs whenever a solid surface is exposed to a gas or liquid. There are common types of gas absorption at the surface of a solid. First is chemical absorption or chemisorption. The second is physical absorption or physisorption. In case of chemisorption, the reactions are often completely irreversible, as there is a genuine chemical bond formed between the absorbing gas and the surface the gas adsorbs on. In the case of physisorption, as the name suggests, there are only physical, weak van der Waals forces at play. The interactions between the surface and the adsorbing gas or liquid are very weak. They are of low entropy and typically of just a few kilojoules per mole. That makes the physisorption an interesting process for studying porous material, as it's fully reversible and non-invasive process. You can measure it as many times as you want, and no damage is made to the material during the measurements. In 1934, Emmett and Brunauer made their first attempt to use adsorption of nitrogen to determine the surface area of a synthetic iron-based catalyst for the ammonia production. The amount of gas being absorbed as function of the relative pressure at constant temperature, called absorption isotherm, is displayed as a red graph. They noted that the absorption isotherm measured at temperatures near the boiling points of nitrogen were all S-shaped. We can see from the graph that the absorption increases as the relative pressure increases. In this case, the relative pressure is simply the ratio between the absolute pressure and the saturation pressure. At saturation pressure, we have equilibrium between the absorbed molecules and the molecules in the gas phase. And it is impossible to absorb more gas, as it will simply turn into liquid. Emmett and Brunauer measured in liquid nitrogen, which is about 77 Kelvin, and for nitrogen, the saturation pressure is close to the pressure of 1 atmosphere. Now, if we imagine nitrogen molecule as a perfect sphere, we can explain the distinctive shape that Emmett and Brunauer observed. We start with a clean surface. Now, the imaginative nitrogen molecules that are shown as yellow spheres are starting to absorb on the surface. At the initial stage, the sample is only partially covered by a few molecules, and it is very easy to absorb them. Therefore, the amount of gas absorbed grows rapidly. As more and more molecules cover the surface, we will finally reach the point when a monolayer is formed at the surface. The point at which we have a monolayer is commonly called point B. If we'd known the exact location of point B, we could calculate the area covered by nitrogen molecules and the surface area of the sample. However, the desorption process is driven by weak forces, and nothing stops the gas from adsorbing on the surface after the monolayer is formed. Therefore, it's not easy to determine the point B from raw adsorption data alone. The multilayer absorption will continue until we reach the saturation pressure P0. At P0, there is so much gas absorbed at the surface that it is in a constant equilibrium with the gas sphere and we can't absorb anymore. Some notes of caution should be issued at this point though. As the experiments are made at cryogenic temperature, what we are seeing is the condensation of a liquid on the surface until the point we're just in an equilibrium between a liquid and a gas phase. In practice, the microporous samples are not flat, and the surface what they have will be of all sorts of shapes and sizes, as well as having pores, of course. We shouldn't forget that in reality, nitrogen is a diatomic gas, and it doesn't have a perfect spherical shape. Still, it is a very useful model for modeling the absorption. Nitrogen is readily available as it is the most common and cheap industrial gas. It is widely used by researchers in determination of surface area and pore sizes. That means most of literature work for reporting the surface area is done using nitrogen absorption isotherm. How can we reliably determine the point at which we have just a single monolayer? The famous BET equation, named after its creators Brunauer-Emmett-Teller, tries to answer exactly this question. The BET equation is shown here in one of its known forms. Parameter P stands for partial pressure of the adsorbate gas, and P0 for the saturated pressure of adsorbate gas, which is the point when absolute equilibrium is reached and the absorption can't take place anymore. This stands for the volume of gas absorbed, which is often quoted in the volume of gas absorbed per gram of the solid. You should spot that there is a monolayer capacity parameter Vm in this equation, and we want to solve this equation for the Vm. There's also a C value, which is related to the heat of absorption. In practice, when studying the absorption data, we would like to plot a so-called BET transform plot. Typically, it is common to take a few points from the quasi-linear range in the absorption isotherm data. This is the most likely region where we will find point B, or in other words, the formation of a monolayer is likely to happen is marked by a square. We can then plot the transformed BET points as function of relative pressure. We draw a line regression plot through the points on transform plot. The slope of this line and the intercept with the y-axis are our key parameters. From the slope and intercept, we can derive the numerical values of the monolayer volume as well as the constant C. The constant C is proportional to heat of absorption. That means fundamentally C must always have a positive value, which is important to check if the BET data approximation makes sense. For example, if you've got a negative intercept, then you probably took a wrong range for your BET transform plot. If we know the monolayer absorption volume, Vm, we can estimate the surface area of a sample. This is often called BET surface area. The BET surface area is commonly measured per unit mass of the sample, for example in square meters per gram. In order to calculate the surface area apart from the monolayer volume, we also need some commonly used constants, like Avogadro number, Na, the normal volume of a gas under ambient conditions, MV, as well as the sample mass, M. Finally, we also need molecular cross-sectional area of the adsorbate, AM, that's the diameter of your imaginative sphere. Nitrogen is the most common adsorbate used nowadays in the measurements of absorption isotherm, and it has cross-sectional area of 0.162 nanometers square. I've talked about absorption isotherm plots, but in some cases, the desorption can be as important as absorption. Let's take a look at absorption and desorption isotherms that have been recorded on tin oxide during my own research. In this case, the tin oxide nanoparticles were prepared by hydrothermal route, and they formed a macroporous material with a surface area of about 40 square meters per gram. As we can see, there is no difference between the absorption and desorption isotherms. We say there's no hysteresis between absorption-desorption isotherms. The reason for this behavior is easy to understand, as the pore sizes are large enough and nothing prevents the molecules to desorb from the surface. This type of adsorption isotherm is called type 2 isotherm according to IUPAC classification, and it is a distinctive isotherm for a macroporous material. Quite importantly, the shape of the absorption and desorption isotherm is related to different pore structure of solids and often can be used as a fingerprint for definition what type of nanostructured materials we have. We will expand on this quite interesting phenomenon in the upcoming lectures. To wrap up, there are three types of nanoporous materials: microporous, mesoporous, and macroporous. We looked at the absorption of gases at the surfaces, which considered one of the most common ways for assessing the surface area of macroporous materials. We've got familiar with the BET equation, and we've seen how it can be used in practice. Now, the important take-home message from macroporous materials is that all these pores are significantly larger than the size of the molecules absorb. That means the gas molecules approaching the surface of macroporous material will consider it as a flat surface, and this have an implication for the shape of the desorption curve. When isotherms are measured on macroporous materials, there's practically no difference between the absorption and desorption isotherms. This brings us to the end of the lecture. Thank you for watching.